We've been talking a bit about probability, and I emphasize that this topic is looking at the relationship between probability and what we call functions, right? We've looked at functions since year 11, and it's this idea that, we can use f of x to represent the graph of anything. So you may be thinking, hang on, why do graphs have to relate to probability? The way I want to start this off is I want to think about how you've normally thought about probability. Like usually you said, okay, let's take a spinner for example, right? And let's say there are like 10 of these segments. Yeah. And I can say that the probability that I'll get any one of these outcomes would just be 1 over 10, right?
Yeah, but it wouldn't be because they're not even.
That's true. So that's when we do one of these. If they don't look even on the paper, then we do one of these ones. That's what I usually do, right? So that's how we've usually thought about probability, in that we have these discrete things. Now, graphically, when we have discrete things, we can use histograms or we can use like bar charts and things like that. The way I want to make this as an analogy to you is I recently encountered this game, which you may have heard of. It's called What Are the Odds? Have you heard of this game before?
What are the odds? I've heard of it.
Right, so it's called What Are the Odds? So the idea is, let's say you and someone are looking at a situation and you're thinking, there's no way that this guy would do this. It's essentially like a dare, right? There's like no way that this guy would do this thing. And the rules are, if you say, Harry, for example, if I want to ask him something like absolutely crazy, something that he would never do, like, hey, what are the odds you do your homework tonight? So you have to give me a number. 1. Okay, 1's a bad example, because what's going to happen next is basically we have to say a number between 1 and the number he's picked. And if it's the same number, then he has to do that thing. So, do you want to pick another number? 2. Okay, sure. 2. All right, then you get someone to count us down. So, James, count us down. So 3, 2, 1, then we say. I don't know. I was indecisive. All right. So you say 3. No, you count down for us. And if we say the same number, Harry has to do his homework. Okay. All right. Okay. So 3, 2, 1. Then we say. Yeah.
3, 2, 1.
1. Oh no! That means you have to do your homework. So if we say the same number, then we have to do that thing. Does that make sense? Right. That's the idea behind this. Yeah. The idea is, if you pick the number 2, there's a 1 in 2 chance. There's a 50% chance that we pick the same number. We can actually quantify that as a particular value. But I want to suggest that this is not always possible. Now you may be thinking, hang on, why can we not do that? Because what's the definition of how we get this? Like, this is very intuitive, but what's the formal definition? And that's the number of favorable outcomes, so what I'm looking for, divided by what? The total of numbers or items. And we call this a sample space, right? So I'm going to give you another situation, another scenario. What if now we're not restricted to whole numbers? What if I can pick any number between 1 and 2? If I can pick any number between 1 and 2, right, what does that really mean I can pick?
Root 5.
I can pick, what is root 5? Put it in the calculator for me. It's like, what? Wait, root 5? That's above 2. 2 point, like 1. 2.1 or something. What's root 3? 1.7. Yeah, when you do trigonometry enough times, you should remember that, right? We can do any other number between 1 and 2. What's another number between 1 and 2?
Root 2.
Huh?
Root 2.
Root 2, which is... Oh, I actually can't remember that one. Oh, nice. Well done. Okay, I should have known that, yeah. Or we could pick... 1.5. 1.5. Yeah, and what's that, Manny? It's infinite. So, what's the chance that me and Harry can now pick the same number if we're not restricted to just whole numbers, but in fact we can pick any number between these? Well, then, going off Maddie's theory, if the number of favorable outcomes, I'm only looking for one thing, divided by how many items in the sample space, how many numbers are there between them, infinity, what does that equal to?
I mean, in theory, it wouldn't be infinity because people wouldn't come up. Psychologically, you probably wouldn't have people go more than like 3 decimals. So, probably isn't infinity.
You reckon?
It's quite high.
James, theoretically.
Theoretically. Can you see the sort of problem we've encountered? I'm highlighting this because before I jump into the mathematics of it, I want to highlight the problem that exists. The problem is, you want to think about you want to think about the chance that a particular thing occurs, right? I want to know the chance that me and Harry pick the same number. That can be quantified when there's a limited number of items. But when you look at what we call continuous data, right? Continuous data is not restricted by the numbers that you are given. For example, on a ruler, check one here. On a ruler, you've got the tick marks on here that represent centimeters and even millimeters, right? But in reality, height is continuous. So your exact height can actually be quantified by a much more specific decimal. In fact, it would probably be a recurring kind of decimal, right? If you're not exactly on one of these tick marks. So this is the problem that we encounter. In fact, if you try and calculate 1 over infinity, what you're going to notice is what's that going to approach eventually? Well, what's 1 over a really big number, right? If you put in a really big number in your calculator. So there's pretty much a 0% chance that me and Harry will pick the same number if we can pick any kind of number here. And this is the concept that I want to highlight. That in a probability density function, now that we're working with continuous data, because there's actually infinite number of things that we can pick here, the chance that me and Harry pick the same number is actually 0, right? So that's something that I couldn't really get my head around. Like, what do you mean it's 0? Like, it doesn't make sense. Like, what if we just pick the same thing, right? What if we just pick the same number, right? But mathematically, for our calculations, the chance that we will pick it, from this definition, the chance that we will pick the same number is actually 0, okay? So what I need you to think about now is, I want to think about the other kind of properties that exist in probability. For example, the chances between that any of the things occur, what do they have to be between? They have to be between two numbers. Or the chance that, like, the probability of a particular outcome, right? If you think about probability, go back to, like, year 8, year 7 probability. Like, the chances that something is picked, right, they have to be between two numbers. 0 and 1, right? Because 0 represents that it's impossible, 1 represents that it's certain. The same property applies for what we call probability density function, or we abbreviate that to a PDF. Yeah, not the do you know what that stands for, by the way? IPT students, anyone? PDF, like the document one.
Something file.
A document file.
I think it's a portable document file. Yeah, that's right. So, yeah. So, what are our properties with? No, don't write that down. What are the properties of a probability density function? Well, here's our curve, right? Where should I do this? I'll do this over here. I'll roll this out.